guys, Bryce here today, and I'd like to talk to you about some common reaction mechanisms encountered in organic chemistry, so you can spend less time here in your professor's office hours and more time mastering the material. Let's get started. Mechanisms can have a lot of steps and are sometimes based a lot on circumstances, which can make them difficult to understand or even know where to start. Luckily, breaking the mechanism down into two simple starting questions will help you determine most of the mechanism. The first question to ask yourself is, what type of alcohalide are you working with? This is determined by the number of carbon atoms attached to the carbon with the leading group. Once you've determined the type of alcohalide you are working with, you must then determine if you are working with a base or a nucleophile. Now this can get a little tricky since bases and nucleophiles are so much alike, but we'll break it down one step at a time. To begin, let's talk about the general characteristics of bases. As a general rule of thumb, bases are typically large, bulky, and heavily sterically hindered, which makes them easy to recognize. A good example of this would be potassium tert-butoxide. Its large, bulky appearance gives it away as a base almost immediately. Nucleophiles, on the other hand, are usually quite small and don't encounter steric hindrance as readily as large bases. A good example of a nucleophile would be sodium hydroxide. However, nucleophiles can get tricky since molecules that act like nucleophiles can also act like bases based on the alcohalide they are reacting with. If you're working with a small molecule, you know it can either be a nucleophile or a base, and in order to know which one it will act like, you must look at the alcohalide you are working with and determine if it's primary, secondary, or tertiary.
So what if you're working with a strong base or nucleophile? Will that change the mechanism the reaction will follow?
Great question. As it turns out, it will. Later, we'll explain exactly how strong bases and nucleophiles will affect the mechanism reactions will follow, but first, let's talk about how to determine if something is strong or weak. When it comes to strength, bases and nucleophiles follow the same guidelines. An easy giveaway that you're working with a strong base or nucleophile is the presence of a negative charge. Another way to tell if something will be strong or weak is by looking to see if an ionic bond is present, as the two elements making up the compound will ionize, leaving you with an anion and a cation. Now that we've covered the basics, we can put that information together to help us determine which mechanism a reaction will favor. Let's take a look at the bulletin board to explain. To begin, let's discuss what would happen if you are working with an alcohalide in the primary position and it reacted with a strong nucleophile. As you can see here, the reaction will favor an SN2 mechanism because the halogens connected at the primary positions will break off more readily, causing the reaction to occur rapidly. Alternatively, let's look at what to expect when reacting a primary alcohalide with a weak nucleophile. When reacting a weak nucleophile, it is probable that the reaction may not proceed, as the nucleophile will typically be too weak to react. On the other hand, let's look and see what would happen if a primary alcohalide reacted with a base. Theoretically, reacting with a base would result in an E2 reaction. However, this mechanism is not favored and will be forced, which causes SN2 to be the most likely mechanism to proceed. Next, let's discuss what will happen when working with a secondary alcohalide. As you can see, when reacting with a strong nucleophile, the reaction will follow an SN2 mechanism, but something interesting occurs when a secondary alcohalide reacts with a weak nucleophile or weak base. In the case of weak bases and nucleophiles reacting with secondary alcohalides, the resulting mechanism the reaction will undergo is both SN1 and E1. Finally, when working with a secondary alcohalide and a strong base, the reaction will undergo an E2 reaction mechanism. In conclusion, when you're working with a tertiary alcohalide and a strong nucleophile, the result is an SN2 mechanism. As you can see, when you react a weak nucleophile with a tertiary alcohalide, the result is an E1 and an SN1 reaction mechanism.
Wait a minute, how did you get SN1 and E1 for a nucleophile? I thought elimination reactions were only for bases.
Great question, Jackson. Let's think back to when we were talking about the characteristics of nucleophiles. One of the characteristics we discussed was a nucleophile's ability to act like a base. When reacting a weak nucleophile with a tertiary alcohalide, we see this characteristic come into play.
Oh yeah, I do remember that. Thanks, Bryce.
Not a problem. Glad I could help. With that being said, let's move on to the next possibility and see what happens when you react a tertiary alcohalide with a strong base. The same rules apply to bases. This is why when you react a strong base with a tertiary alcohalide, the result is an E2 mechanism, and why when you react a weak base with a tertiary alcohalide, the result is an E1 and an SN1 mechanism. So there you have it, all the rules for chemical mechanisms in just over 5 minutes. Now take that information and use it to cut your study time in half and master organic chemistry. This is Bryce, signing off and wishing you happy studies. See you next time!